Good afternoon, everyone. A warm welcome to all of you to the final session of our webinar series on cellular automata. Thank you for joining us in this series, which started in August 2020. On behalf of the organizer, I want to thank you for joining us in this series and making it successful. I also want to invite you to stay after this talk for a brief valedictory session. We had already started this series with a talk by Professor Sukanta Das. On our request, Professor Das agreed to give us another talk on his research at our concluding session. We are delighted that today Professor Das will deliver his talk on a characterization tool in the age of cellular automata technology. Although he is revered in his field, as is the custom, let me first introduce our speaker. Professor Sukanta Das currently works as the head of the department and associate professor in the Department of Information Technology in Indian Institute of Engineering, Science and Technology, Shibpur, formerly known as Bengal Engineering and Science University, Shibpur. He received his PhD in 2007 from Bengal Engineering and Science University, Shibpur, and Masters in Engineering in 2002 from Bengal Engineering College, which is currently known as the IST Shibpur in Computer Science and Technology. He joined his alma mater as a faculty in 2003. He has been doing research in the different aspects of cellular automata for more than 20 years. His research area includes cellular automata theory and applications. He is also a member of the IFRP Working Group 1.5 on cellular automata and discrete complex systems, and several programming committees for international conferences on cellular automata. He has more than 70 articles under his name. Currently, he is exploring the computational abilities of cellular automata, the non-uniform cellular automata, partial number conservation in cellular automata, reversibility and cycle structures of cellular automata, chaos and randomness in cellular automata. Apart from the research, Professor Das is also an active member of the Science and Rationalists Association of India, a rationalist organization dedicated to advocate against pseudoscience, astrology, and mysticism. He is known for his active role in science awareness in common people and school children. So we are eagerly waiting to listen to you, sir. Over to you.
Thank you, Kamalika, for your introduction. Is my screen visible?
Yes, sir.
Okay. Just okay. As Kamalika has introduced, today's topic is reachability tree, a characterization tool in the age of cellular automata technology. So, before going to that part, cellular automata technology, let me first briefly recall what a cellular automaton is. A cellular automaton is a quadruple. It's quadruple J to the power D, S, M, and R, where J to the power D is a d-dimensional lattice. We call it cellular space, and S is a finite set of states, and M is called neighborhood vector, say V1, V2, Vm. So they're the M elements of J to the power D. They're generally they are the neighbors of a cell. Say suppose my cell is V, vector V, and then so the neighbors of the cell V I can get as vector V plus vector Vi. So they're the neighbors. So M defines the neighborhood vector of the cellular automaton. And finally, the rule R. So this is actually for M to S, where this M is actually the number of neighbors of a cell. So is the transition function, we popularly call it local rule of the CM. So a cell automaton is a discrete system. It is discrete dynamical system. Here, space and time both are discrete. And in case of solar automaton, we get some configurations. Configuration is nothing but mapping from J to the power D to S. It's an assignment of states to some cells. We call it configuration. And so, what we get actually, we get that a CA, a cellular automaton, it hops from one configuration to another configuration, right? So if I give one input, then from that input I get the next one and next one, etc. So from this definition, I can get a transition function, say we call it global transition function G. Different from a set of all configuration to set of other all configuration. So this is the global transition function. Sometimes we identify C by this global transition function. And how to get this the next configuration? Suppose C dash is the next configuration of a C, then C dash is equal to G of C, and this is computed in this way. We can get C dash in this way. That is, what does it mean? So it means that when a configuration is there, so each cell applies the local rule R to go to its next state. So see, and all the cells apply the local rule parallelly. So from one configuration, we get another configuration. So this is the classical definition of a cellular automaton. And cell automaton was first developed. The credit goes to generally John von Neumann along with Stanislaw Ulam, who wanted to study the mathematical model of biological self-reproduction. So for that purpose, uh, von Neumann proposed this cellular space, and his space was two-dimensional, and he showed that okay, it's possible to mathematically model the biological self reproduction, and this work has a great impact on the mathematical biology. Although it was initiated by von Neumann, but it was popularized by John Conway, a famous mathematician who died in last year out of corona. He popularized the solar automaton, and his famous work, Game of Life. So it's very simple, a two-dimensional game. He took two-dimensional space, and only two states were there, alive and dead. And he proposed simple rule where he showed that using that simple rule, it's possible to generate, possible to model self-reproduction and very many other interesting properties. Anyway, apart from this modeling of self-reproduction and self-organization, solar automata have been studied by researchers for many reasons. So, such as it is considered as this model is considered as natural model of computation, and they are capable of doing universal computation. Since solar automaton is a discrete dynamical system, so it is a tool of study the chaos. So solar automata they are being used to study the chaos, and obviously several natural phenomena they are modeled by solar automata, and there are many more. Okay, it is claimed that solar automata, the natural model, it's a natural model of computation, as I've said. So these are the theoretical work on cell automata, which the mathematicians, the computer scientists are doing over the decades. However, in all the cases, what we need infinite lattice. So in the definition, we have seen that it is j to the power d. So lattice size is infinite. So cell automata, and they are defined over infinite lattice. Now, apart from this theoretical interest, some researchers, especially some engineers, so they explored solar automata as technology. Not only on the theoretical aspect, they have said that okay, solar automata can be treated as technology. So by technology, we mean a collection of techniques. This is a classical definition of technology. It's a collection of techniques, methods, or process used to provide some services or solution to problems or accomplishment of an objective, such as scientific investigation. So cellular automata, so this class of researchers, they show that cellular automata, okay, this is the model of computation, but they can be a technique, a collection of technique. I mean, they can be treated as a technology. And the work started from late 1980s, and so some target applications were there. The pseudo number generator for pseudo number generation. So cellular automata have been used, especially in the era of VLSI. VLSI means very large scale integration. So for VLSI circuit design and test, cellular automata, have been used. And it's a very popular one. Cellular automata is a very popular tool to provide some solutions for VLSI test problems, as well as to design some security system, okay, as and pattern classifier, pattern recognizer, image compression, image processing. For several applications, people have tried uh, uh, this cell automata. And cell automata been established, as a good tool to handle these problems, this real life problems. However, in the just now we are talking about infinite CA, but to address this kind of problem, we need finite cell automata, because we have to implement a cell automata on some machine, maybe in software, maybe in hardware, but that should be finite. So in case of when we model it, I mean when we use the cell automata for some application, we cannot deal with the infinite lattice size. So we have to come back. We have to consider the finite lattice size. So this is a finite cell automata. Finite cell automata, same definition. So it is a quadruple L, S, M, and R as usual. But the only point is the lattice size, three-dimensional lattice size L. It is to be finite. This is the only property. Since it is finite, so there's some end, right? So some cells are at the boundary, so I can find some boundary cells. So therefore we need to specify boundary condition. In case of solar automata, two special boundary condition, two boundary conditions are popular. One is open boundary condition, other is periodic boundary condition. So in case of open boundary condition means missing neighbors assume some specific state. So this is a diagram of open CA with open boundary condition. I have considered here one d equal to 1 means one dimensional cell automaton. So it's an open boundary condition. So here a special type of open boundary condition I have shown in the figure is called null boundary condition. Means in the left side of cell 1 as well as right side of cell n, I have assumed that they are always getting state 0, null. So it is commonly called as null boundary condition. On the other hand, in case of periodic boundary condition, it is considered that lattice, that is spatially periodic, right? In case of one dimensional cellular automaton, so the cells form a circular array, right? So these two popular boundary, these are two popular boundary conditions. Well, now there's one more point. See, let me now introduce the hybrid cell automata. See, in the classical definition, what we consider that all the cells use a single rule. That's called uniformity constraint, right? Means all the cells, they use uniform rule to go to the next state, right? Now, if we, disobey this rule, if we allow the cells to choose different rules, then it becomes hybrid cell automata, also called as non-uniform cell automata. From the very beginning, the researchers who used cell automata for application purpose, they used this kind of hybrid cellular automata or non-uniform cellular automata. In particular, they have used non-uniform ECA, elementary cellular automata. What is this? It's a finite cellular automata with Wolfram rules. I mean, the cells will use Wolfram rule. Note that Wolfram CA is a one-dimensional CA. So therefore, non-uniform ECA is also one-dimensional ECA, and this is the most studied cellular automata for application purpose. I mean, almost all works, not all, but almost all works, they have considered non-uniform ECA. Why it is so? Because of simplicity. If you consider software implementation, hardware implementation, anything, so non-uniform ECA, they are easy to implement. Okay, so and it was shown by Stephen Wolfram in early 80s that ECA, the simple rule, it's the rule is like this: a cell depends on only left neighbor as well as right neighbor, and the cells use two states, 0 and 1, binary system. But still, this simple system, can show excellent behavior. They can show chaotic behavior. They can perform universal computation and so many things. So, although ECA they are very simple, but they are having nice properties, complex behavior they can show. So, people targeted this non-uniform ECA to use them for application purpose. So at this stage, one question may be asked: why not uniform CA and why non-uniform CA? See, from the application point of view, when you will implement this kind of cell automata in software or in hardware, then it doesn't matter whether the cells are using same rule or different rule. So therefore, from application point of view, this non-uniformity does not put any extra burden. Further, you'll have several options. Your option will be high, and it is also observed that in nature, so what you see, they are not always uniform. So people argued that okay, better to use non-uniform CA for application purpose. And we know there are there are many properties which we can observe in case of non-uniform system, but we don't see in uniform system. Anyway, finite non-uniform cellular automata have been used to have been used for technological purpose. For this kind of system, we need a special thing called rule vector. What is that? Since the cells are using different rules, so therefore, which cell is using what rule, that you have to specify that one. For this, we need a rule vector. Say, take an example. Say four cell non-uniform CA 150 90 150 90 is a four cell automaton with these rules. First rule is using 150, second rule is 90, 150, then 90. Now, what these numbers are? These are nothing but a rule. Actually, classically, so rules, are represented in this fashion. This is a Wolfram rule. So, as I've said, Wolfram rule is just it is binary system, and the cell depends on left neighbor, self, and right neighbor. So, three neighborhood. So you have 0 0 0 to 1 1 1 these options, and for each option, I am writing down the next state value against the function. So then I can get a binary string which actually defines the function. So this tabular representation of a function of a local rule is very popular, and this decimal equivalent of this binary string is called as rule. So this is 150, this is 90. So in this four cell non-uniform ECA, so first cell is using 150, then 90, then 150, then 90. Now, how it executes? Sorry. Now, suppose this is my cell. So just example I have given. Suppose my initial configuration is 0001, and next clock means in next time, what I get? So this cell 0, it applies 150, and this cell, second cell, it applies 90, third cell 150, and fourth cell 90. And here null boundary condition is used, and using that one, I can get from 0000 0001, I can get the configuration 0010 From that, I can get 0, 1, 1, 1. In this way, I can get the configurations and next configurations and see a cell automaton evolves. So let me introduce a class of cell automata, which are called as linear cell automata. See, from onward, we shall mainly concentrate on non-uniform elementary cell automata. From non-uniform elementary cell automata, there is a class of cell automata which are called as non-linear cell automata. So linear is if the rules are linear. So if the rules are linear, then that cell automaton is called linear cell automaton. And there is a special class of automaton, especially we find in case of binary system, called complemented cell automaton. What are they? If at least one rule is complemented in the rule vector, then that CA is called, and the rest are the linear, then that CA is called complemented cell automata. And what is the property of linear cell automata? In case of ECA rules, if a rule can be expressed in XOR logic, means modulo 2 operation, right? For example, rule 60, if my rule is if I have three arguments x, y, z, then rule 60 is nothing but x plus y mod 2. Rule 150 is x plus y plus z mod 2. So if I can express the rules in this fashion, this is linear. And its complemented is, if it is complementation of a linear rule, the rule is complemented rule. So these two classes of rules are classes of CA, linear and complemented. They are of special interest due to some reason. However, apart from that, the rest rules are non-linear rules. There's a huge rule. Only you can, 8 rules are linear, so 8 are complementary rules. So out of 8 plus 8, 16. So 240 rules are non-linear rules. And a CA is non-linear if one rule is non-linear, then the CA becomes a non-linear CA. Okay, come back to that part, cell automata technology. So in case of cell automata technology, the technologies are developed around two classes of CAs. One is reverse level CA, and this convergent CA. And in case of what is reverse level CA, where all configurations are cyclic. Okay, from if you start journey from one configuration, the system will come back to that configuration after some time. Whereas in case of convergent CA, if you start journey from one configuration, you will reach to one particular configuration and say some fixed point. So these two classes of CAs are of interest of researchers. And the applications, there are, for pseudorandom pattern generator, for VLSI circuit design, for cryptography, the reversible CAs are used, whereas for pattern classification, recognition, image compression, image processing, so convergent CAs they are used. So let me briefly describe some technologies, okay, some applications of cell automata. So I shall quickly go to the slides. So it's a pseudo-random number generator. So cell automata, they are used as a good pseudo-random, and they have been used as a good pseudo-random number generator. Pseudo-random numbers are the numbers which are not actually random but appear to the users as random. So in case of CA, out of configurations, we can generate the numbers, and the pseudo number generators, they should follow some property, for example, uniformity, independence, large period, etc., etc. And if I want to develop a pseudo number generator using cell automata, what is my requirement? My requirement is I need reversible CA. Okay, and reversible say that the cycle should be high, so large cycle is needed. If I want to satisfy these properties, so at least my primary requirement, CA cell automaton should be reversible, and the cycle length of the reversible CA should be high as possible. And classically, maximal and CAs are used to design random pseudorandom numbers. Maximal and CAs are special class of CAs where all the configurations, they are in single cycle except one. So this is an example of maximal and CA. You can see except all 0 configuration, all the configurations, rest configurations, they form a single cycle, right? So if you start from any one configuration except 0, then you'll see all the patterns. So it may appear to the user as if the new number, the numbers the system is giving to you as as random, as pseudo random. So pseudo random number generation, for the pseudo random number generation, C have been proved very good and a good tool. Apart from Civil Automata gained its huge attention, in the domain of VLSI design and test. I'm not going into detail, but for VLSI circuit design, especially test logic design from the in 1980s, since 1980s. So CA, Civil Automata, they have been used. And for just few words, there's a word called BEAST, built-in self-test, for which is used for VLSI circuit test. For BEAST design also, Civil Automata, we can use Civil Automata. We can use PRPG, pseudo random pattern generator, okay, for testing purpose. So just what is BEAST? So BEAST has 3-part TPG, Sagirana test, and response analyzer. And this TPG part called test pattern generator. This test pattern generator, some patterns are generated for testing of some circuit, some hardware. So these test patterns can be generated from the Civil Automata. See, if my Civil Automata is binary Civil Automata, if I use non-uniform ECA, so it generates some configuration. So they are all binary. So these binary configuration can be considered as pattern. So TPG, for implementing TPG, so Civil Automata, they are used. So just I have written some kind of test patterns. There are several kind of test pattern. Let me skip this slide. So Civil Automata, its great advantages. Civil Automata can be considered as universal pattern generator. For testing a circuit, sometimes you need pseudo random patterns. Sometimes you need pseudo agnostic pattern. Sometimes you need pseudo random pattern with prohibited pattern set. Sometimes you need deterministic test pattern. So you may need several kinds of pattern. So important thing is Civil Automata is capable of generating all kinds of patterns. So people have proposed Civil Automata as universal pattern generator. Okay. So this is the other application, and the very interesting application, but I am skipping for time constraint. So I can design test pattern generator without pattern set. Simply in 2 words, few words, I can say that I want to generate some random patterns, but I don't want to get some set of patterns. I want to exclude some set of patterns. That pattern I don't want. Okay, that pattern set is very small generally. So point is I have to develop a system, develop a generator which generates pattern, but does not include that the pattern generated by the system does not include the prohibited patterns. Okay, it's a very interesting problem, and that problem can efficiently be solved by cellular automata. So design. So next important application is pattern classification. So there is a one class of Civil Automata called MACA, multiple attractor Civil Automata. So it's a special class of Civil Automata where it's actually convergence CA. Okay, where all configurations. Okay, so if you start from any configuration system, your CA will converge to some fixed points. We call them attractor. So I have given one example. Suppose there's 4-cell CA with this rule vector, and if you can see there are 4 attractors, 3. So attractors are written in the configurations are written in decimal format, decimal equivalent. So you can see there are 4 graphs. S1 we call it basin of attraction. S1, S2, S3, S4. Now, if you start from any configuration, you can start from 4, you can start from 12, you can start from 6. In all the cases, the system, the cell automaton, will converge to a fixed point. So this kind of cell automata, they are called MACA, multiple attractor cellular automata. And this kind of cell automata, they are very useful for doing pattern classification. How? I'm giving one example with this. So suppose I am to develop two class classifier. So class 1 and class 2, and somehow I know that the basin S1 and basin S2 they form class 1, and basin S3 and S4 they form say class 2. How I know this? From my training or from my previous knowledge I know. Now, if I store this information, the 3, 7, 15, and 11, all is attractor, and if I have the machine, then you can start from any configuration. You know, you'll reach to some particular attractor. Now, if you know the 3, attractor 3, it represents class 1. Attractor 15, it represents class 2, and so on. Now, suppose you start from 4. Now, if you start from 4 and if you reach to 3, just looking at this 3, you can say, okay, this pattern means the initial pattern 4, it was of class 1. Or if you start from say 9, from the 9 you will reach to from 9, so you will reach to 11, and you know from your stored information you know that 11 represents class 2, right? So these attractors, they are the representative of class. By storing this representative and by running the machine, you can understand, you know, you can decide the class of input configuration. So this is useful, useful for pattern classification. Well, so what I've said here, I've given few examples. I've started with pattern, pseudo-random number generation. Then I've given an example. I mentioned the VLSI for VLSI circuit design. They are being used. Then I have said then pattern classification, etc. You see, for different applications, requirements are different. For example, in pattern classification, what kind of CI I need? We need multiple attractor cell automaton. Obviously, when a cell automaton or rule vector is given to me, that may not be my this multiple may not be MSCA. So question is, how can I know that whether that my input cell automaton is really my required cell automaton, or in other words, how can I synthesize? How can I get that configuration? Get the required cellular automaton. That is a great challenge. So these are computational difficulties. So problem is, decide if a given N cell NUCA, non-uniform CA, is reversible or converging CA. Okay. Obviously, this problem is resolvable. Because you are dealing with finite system. But how can you manage it? Can we do by exhaustively running the system? Suppose you have arbitrary, suppose n equal to 100, and you are using non-uniform cell automaton. Each cell can use any one of any rule. And if you use Wolfram rule, there are 256 number of rules. So therefore, how many CAs you can have for n equal to 100? 256 to the power 100 number of cell automaton. From that, you have to choose some good one, some good candidate for solving your problem. That is really a big challenge. I think you all understand how big the number is. 256 to the power 100. And 100 is not a big number, a really very small number. If you want to do it exhaustively, then you have to deal with this 256 to the power 100 numbers. So this number is very, very big. Practically impossible to deal with. Okay, so I can give one analogy that, it is estimated that number of atoms in universe. How many atoms are there in our universe? Universe means observable universe, the universe which you can observe. So it is 10 to the power 78 to 10 to the power 82 only. And your number of cell automata for n equal to 100 is 256 to the power 100. So it's simply not possible to exhaustively explore, exhaustively check and decide, okay, which are your required cell automata. So therefore, you need some technique if you really want to use this cell automata for your technological purpose. There's a good news for linear and complementary cell automata. I mean, which I mentioned in a few slides before, they can be characterized easily by matrix algebra. This is the really good news. By just analyzing the matrix. So for that class of CA, I can represent the system. I mean, I can represent the automaton, cell automaton by some matrix, and by analyzing the matrix, I can discover many properties. Okay, so then we can use the standard known results of matrix algebra. Okay, for example, so I have given an example that 90, 150, 90, 150, this is my 1 4 cell CA. That CA can be represented by this matrix. We commonly call it T matrix. So this T matrix is under null boundary condition. So how I'm not going in detail how we can get this kind of T matrix. It's possible for any kind of linear CA. It's possible to get this T matrix. Now, once you get T matrix, you can decide whether the input C is reversible or not. How? Just by finding the determinant of the tree. If it is 0, then reversible. If it is not 0, then reversible. Okay, it's a good news. But if you use nonlinear C, any query? Okay, but if you use nonlinear C, see, for the betterment of the result, to get a better result, we'll always try to use all rules, all possibilities. You'll try to explore. But if you want to use nonlinear C, you have no way. You had no way. And for that, a reachability tree, has been introduced. So now I shall go to this part, reachability tree part. Actually, this is the topic of today. So for going to that part, I need some introduction, but I'm quickly going through this. So there's a concept called rule mean term. So this term will be used to define a reachability tree. Rule mean term is nothing but the argument of the function of the rule. Okay, so this is my rule. Say this is the rule table. Say 165, 73. So the ECA and the Wolfram rules. So there 0, 0, 0, 0, 0, 1, 0, 1, 0. You can see as argument they are the RMT or rule mean term. Okay, so and they are generally represented by their decimal equivalents. Okay, so like 0, 0, 0 is 0, 0, 0, 1 is 1, 0, 1, 0, 2, and so on. There are some configurations which we call reachable configurations, some configurations which we call non-reachable configuration. So a configuration is reachable if it is reachable from some configuration. It is non-reachable if it is not reachable from any configuration. In the figure you can see 0, 0, 1, 0 is non-reachable because you can reach in this configuration from any other configuration. So similarly 1, 0, 1, 0 is again non-reachable configuration, whereas 1, 0, 0, 1 is reachable configuration. 1, 0, 0, 0 is again a reachable configuration. So this is the reachable configuration and the non-reachable configuration. These two terms will be used while you define the reachability tree. So configuration. So as usual, configuration here, we are considering configuration as a sequence of states, the 0, 0, 1, 0 configurations. And see this diagram. So this diagram is a special name. We call it transition diagram. It's obvious. So from one configuration where it is moving, that is noted down here. So this kind of configuration is called, this kind of diagram is called transition diagram, which we'll again use. Sometimes configurations, they can be represented as a sequence of RMTs, right? It's another way of presenting configuration. Sequence of RMTs where this RI, say configuration C is given, and this is the C tilde, this is the RI, where RI is actually RMT. Okay, so RI is RMT of the argument. So ith cell is using the one rule. The rule has a function that is one argument. That argument, that is called the RMT. RI is this, RMT this one. Okay, so how many RMT sequences are there? That is equal to number of possible configurations. Okay, so RMT sequence and next configuration, you can think of a pair. So you know the RMTs, RMT sequence for one RMT. If you consider this rule, this table, from one RMT, you get one nested value. Okay, so from the RMT sequence, you get a next configuration. For example, 0, 1, 2, 0, 0, 1, 2, 0. So from 0, 1, 2, 0, if you consider this nonlinear CA, nonlinear non-uniform CA, 165, 73, 290, and if 0, 1, 2, 4, this IMT sequence is given. From this IMT sequence, you can get 1001, this configuration. You can see here that from IMT 0, this IMT 0 is 1, IMT 1, IMT 1 means IMT 1 of second rule, this is 0, you are getting 0 here. Then IMT 2, IMT 2 of third rule, IMT 2, yeah, it is again 0, I am getting 0 here. IMT 4 of the fourth rule, IMT 4, yeah, it's 1. So 1, 0, 0, 1, I am getting this pair. So IMT sequence and next configuration, they form a pair, predecessor successor pair. It has also a role in defining the reachability tree. Now, reachability tree is nothing but a tree which represents all reachable configurations of a CA. It practically depicts that IMT sequence and configuration pair that it actually does. Reachability tree depends on number of states. If your CA is, we use binary CA, then reachability tree becomes a binary tree. If we use three-state CA, a trinary C, and so on. If I use D-state CA, then DRS, it'll be DRS, tree. So our interest is non-uniform ECA, non-uniform ECA. So therefore, my system is binary. So our reachability tree is binary. In my discussion, I shall also consider binary reachability tree. And one more thing, boundary condition is also important to define reachability tree. So in my case, I shall use null boundary condition. If I want to use periodic boundary condition, structure of tree will be different. So here I am using null boundary condition. And let us consider my CA is 165, 73, 290. This is my rule vector. And I want to get reachability tree of this CA. And if there are n cells in a CA, then there are n plus 1 levels. So it's four cells are there. Yeah, there are four cell 160, 165, 73, 290. So there are 5 levels, and this is my reachability tree. See, before going to the formal definition, just let me explain what does it mean. See the nodes and some edges, obviously. This is the edge level tree. And the nodes are nothing but set of RMTs. In null boundary condition, root node consists of always these 4 RMTs, 0, 1, 2, 3. Okay, 0, 1, 2, 3. Now, from 0, 1 to 3, so I get this node, I get 2 children on left child and right child. How I'm getting? See, here it is written 1, 3. What does it mean? That this level left edge coming from the root node, it is labeled by 1, 3. This 1, 3, if you observe, you can see that for 165, RMT1 and RMT3, they are 0. RMT1 and RMT3, they are 0. So left edge, always we call it 0 edge, right edge 1 edge, and this 0 RMT, this value 0 is coming from 2 RMTs, 1 and 3. So I have written 1 and 3. In this case, it's 1. So IMT 0 and 2 of 165, it is given, say 0 and 2 is giving 1, so it's 1. Right? Now from 1, 3, I am getting this next node. How this next node? See, it's 1, so I'm getting 2 and 3. 2 into 1 plus 1. So 2 from 1 I'm getting 2, 3. 3 I'm getting 6, 7. Okay, so 2, 3, 6, 7. From 0 and 4, from 0, 2 into 0 plus 1. So 0 and from 0 I'm getting 0, 1. From 2 I'm getting 4, 5. Okay, so these two nodes. Now these nodes, they're having some RMTs. These are the RMTs of second cell and second rule. So from these RMTs, I can get again, say for consider this, leftmost, I mean leftmost node here, 2, 3, 6, 7. It is having also two children. So one is left and another is right. So for the left child, 2, 3, 6, say 2, 3, 6, 7, I am getting say 2 and 7. I am writing here 2 and 7. Why? You can see 7 and 73. IMT 2, it is giving 0. IMT 7, it is giving 0. So 2 and 7, I am adding here 2 and 7, it is giving 0. And here 3 and 6. So 3 and 6, they are giving 1. So I am adding 3, 7. Okay, so in this way I construct. But there's a point that, see, look, consider this one, 0, 1. Consider this node here, 0 and 1. Say this RMT is the RMT of first rule, second rule, third rule, means RMT of 200. This 0, 1 is the RMT of 200. Now the node consists of only two RMTs, 0 and 1, and this 0 and 1, see, both the RMTs are 0. Well, I have written in the left side, it is 0, 0 and 1. Okay, but nothing is for the RMT 1. Say, sorry, no RMT is left. So I cannot get this right edge, right? There is no right child. So this node is having only single child, right? So this does not exist. So I have written, I have put here a dotted line. So this is actually non-reachable edge, and this is non-reachable edge. We call it non-reachable edge, and this is non-reachable node. Actually, they don't exist. So this is a roughly reachability tree. This reachability tree represent reachable configurations. Why? See, the number of leaves, actually number of reachable configuration. See here, 0, 0, 0, 0 is reachable configuration. 0, 0, 1, 1 is reachable configuration. But 0, 0, 1, 0 is non-reachable. And in this way. So it's very simple. It's nothing but it represents reachability tree represents a reachable configuration of a cellular automaton. Its formal definition looks a bit complicated, but this is the basic idea. So this is the formal definition. It's a edge rooted and edge labeled binary tree with n+1 levels, and these are the conditions which are followed by the nodes and edges of the tree. So what I've said, that is written here. So I'm not going into detail. So okay, I have explained non-reachable edge and non-reachable node. Okay. Okay. So few results. Lemma 1, lemma 2 is interesting. So what it looks like, the tree grows exponentially, right? It starts from root, from the root to 2 nodes, again 2 to 4 nodes. So it grows exponentially. However, interesting point is, so number of unique nodes are very limited. In case of this CA, lemma 2 is saying number of unique nodes at a level of the tree of a CA and a null boundary condition is less than 15. So it is bounded by bounded by 15, and and from that I can get some theorem that there exists an efficient algorithm to find out total number of non-reachable configurations of a finite CA. So I'm not going to detail. I have taken so much time. So anyway, so I'm not going to detail of this theorem at the proofs. So this is reachability tree. So this reachability tree can be used to to decide reversibility of a CA or convergent of a cellular automata. Convergence of cellular automata. Okay. Reachability tree and reversibility. So now we are going to explore how we can use reachability tree to decide reversibility of a cellular automaton. So first theorem is reachability tree of a reversible CA is complete. So it's very simple theorem. So in case of reachability tree, in case of reversible CA, all the configurations they are reachable. So tree is complete. So this is an example. So this is a reversible CA, in fact, 90, 15, 85, 15. So you can see that all configurations they are all the configurations they are reachable, right? So this CA is reversible, and there is a theorem. So next theorem is if the reachability tree of an n-cell CA is complete. I mean, if the if it is a tree of a reversible CA, then the level of age, number of element, number of RFDs in each level, it is 1 if it is the I equal to n-1, okay, or 2, exactly 2 if I is less than n-2. So here you can see in this figure, see this 0 2, they're the levels, 0 2 0 2, they're the levels. So 0 to here is level, 1 to other level. See, you can see always 2 levels are there, right? These 2 levels. But for the last one level, 6 2 4 0 6. You can see only single level is level is there. So that is saying this theorem is saying that one. So it has another implication. At any point of time, when I'm constructing the tree, if I see that I'm getting a level, I'm getting an edge with level more than 2, with more than 2 or more than 2 or less than 2. I mean 1 or more than 2 RMTs, then we can declare that okay, the CA cannot be reversible. This is the implication of this theorem. So, okay, we can prove the theorem by induction, but I am not doing here. So it's a corollary that if the tree is complete, then the number of elements in each node, it is 2 if I got n-1, if I got n-1, or 4 if I less than n-2. So for this one, so here we are having always four RMTs. You can see each node is having 4 RMTs, but here see there is a small mistake actually. Is 2 3 6 7, actually 3 and 7 they can't exist. It will be 2 and 6. Similarly 0 1 4 5, 1 and 5 cannot exist. Here it will be 0 and 4. So they will be these nodes will consist of 2 IMTs only. One more thing, the some rules are the balanced rules. The rules are balanced, means if number of zeros and number of ones, they are same in a rule, in a binary string of the rule, then the rule is called balanced. And theorems are there, we can prove it also that if any rule is unbalanced, then CA cannot be reversible. So important theorem. Okay, and each node of a reversible CA is balanced. Okay. And the fact is, as I've said, that at each level except root, unique number of node, unique number of node of a CA on a null boundary condition is either 2 or 4. So very important thing. No matter how tree is going, so no matter how what is the size of tree, it may grow exponentially. It may grow exponentially, but so number of nodes only 2 or 4. So using these 2 or 4 nodes, if I can manage only, if I can develop some algorithm which deal with these unique nodes, right? Then so I have to deal with only 2 or 4 nodes, only very few number of nodes. Okay, so using this fact, we can develop our decision algorithm. How you can decide? So you deal with either node or edge, right? If you deal with edge, very good. You start from root. It will have 2 children, so 2 edges you will have to 2 levels. Each level, as the theorem is saying, each level will have only 2 RMTs. Okay, and then you start with first level, then from that level you get levels of next level edges. In this way, you may start with node also. Our caller is saying each node will consist of 4 IMTs, so root is 4 IMTs by default. Then from the root you compute the RMTs of nodes of next level. If you find that any node whose number of RMT, the size is less than 4 or greater than 4, you can declare CA is reversible. See, I need not to store, I need not to backtrack. Okay, I have the theorem, so I'm not backtracking. So therefore, I am storing the old information. So from one node, I am getting only the next level nodes. Now, since number of nodes either 2 for reversible CA or 4, so I have to deal with at max 4 number of nodes in each level, right? And if at any point of time, if I find that my theorem is violated, I can declare that cell automata is not reversible, it's irreversible. Otherwise, if I be able to proceed at the end, I'll declare the CA is reversible. Simple. So its complexities, obviously order of n is very fast, very fast. Similarly, we can synthesize reversible CA. You can design reversible CA, right? So it is sometimes required that sometimes you may ask, okay, give me some reversible CA. That also can be done by exploring this reachability tree. How I can do that one? I can randomly fill up the RMTs so that the conditions just you have stated, they're satisfied. Okay, and based on that, I am internally developing that. I'll internally develop the tree. My condition is I have to obey the conditions of reversibility. The theorems are to be satisfied. Now, if I can proceed in this fashion, then I'll be able to synthesize a reversible CA, right? So synthesis of reversible CA, it is also very simple, and its complexity also order of n is very fast. No matter what is the value of n, you may put 100, 1,000, 1 billion. So it's very fast. Okay. Well, so what the previous discussions have shown, that by a tool has been proposed called reachability tree. Using the reachability tree, we can decide reversibility efficiently, right? Although I have shown the result for null boundary condition, similar result you can find, I mean, they are actually for query boundary condition. Similar result you can get for other, say, distant CA, etc. Now, let us deeply look at the rules which are actually forming the reversible cellular automata. Okay, so as I've said, the ballast rules can only form reversible CA. You have some theorem, so that I have stated. So let us deal with the ballast rules. So the theorem is there that a non-uniform CA with an unbalanced rule in its rule vector is irreversible. The proof is very simple. I have not stated here. So therefore it means to get reversible CA, you need always balanced rules. But you have 70 balanced ECA rules out of 260 and 256 number of rules. You have 70 balanced ECA rules. Under null boundary condition, the fact is only 62 balanced rules can participate in rule vector of a reversible CA. There's a footnote. If you use periodic boundary condition, then all the 70 rules can participate to form a reversible CA. However, if you use null boundary condition, then you'll find only 62 number of rules which can form reversible cellular automata under null boundary condition. Okay, but the point is, arbitrary arrangement of 62 rules cannot form reversible CA. In fact, if you take these balanced rules, 62 rules, and you arbitrarily arrange the rules, almost always, and most of the time, you'll get irreversible rules. So therefore, first necessary condition is the rules are to be balanced, but that is not a sufficient condition. So you need a specific sequence. Okay. So an example I have given 90, 15, 85, 15 is reversible CA, but the just 90, 85, 15, 15 is irreversible. Just to change the ordering, no, it will be irreversible. So next question comes, when a rule is given, after that rule, which are the possible one rule, which rule can come, which cannot? To address this issue, we have classified the rules into 6 classes: class 1, class 2, class 3. So the basic class, three class, then class 4, then class 5, then class 6, derived from this 3 class. I shall not go into detail. If you're interested, the resources are there in internet. So this resource can be shared later. But the point is, the rules can be classified in 6 classes, which says after one rule, which rule can come, which cannot. And what is the result of this research? This table. This table is saying, you can see the name of rules. So 51, 60, 195, they are the members of class 1. Right? In fact, it's written in this case also. Say class 1. Which rule are forming class 1? Say 51, 53, 54, etc. They are class 1. Class 2, 50, 30, they are class 2. 3, 15, class 3. Observe that one rule may be member of 2 classes. It's not that one rule member of always a single class. Not that one. Actually, class allows what class means. Class means after one rule, which rule can come. Okay. Anyway, so we have this kind of class relationship. If I start with the rule of class 1 and the rule is 51, then class of next rule is to be 1. If I start with class 1 and next my rule is 85, then the next class of next rule is to be 2, in this way. this is, I should say, it's a beautiful relation. So from one class, which class I can go, that is depicted here. But in case of null boundary condition, so boundary cells, they're special always. In case of finite CA, boundary cells are special always. Okay, they are not the ordinary cells. So here, so we need two more tables. One is for first rule table, where from I can start this last rule table, where I have to end. So first rule table, you can see here in first rule table only 6 rules are there: 3, 12, 5, 10. Why? Because in case of first rule, so I have 3 argument. A rule has 3 argument: left, self, and right. Left argument is always 0, right? Left argument cannot be 1. And if I look at the tabular form of the rule, then last 4 are empty. 4, 5, 6, and 7. They are considering left neighbor as 1, which cannot come, which can never appear in case of null boundary condition. So I have considered 1, 0, 0, 4, 5, 6, 7. These are empties as 0. Right? If you consider 1, there is a problem. But for S of representation, we have considered them 0. And so using that one, I get this first rule table. Similarly, the same rationale is applicable for last rule table. So these tables are formed. Then, so from this table, from this table, I can decide whether a given C is reversible, or I can synthesize a reversible CA. So let us see that 90, 15, I have given the 19, 50, 85, and 15. I have said it's reversible. I can check whether it's reversible or not. Say first rule is 90. So for the first rule, I have to consider this first rule table 90. But in my table, there is no 90. But see, 90 is equivalent to 10. Why? Because there is first rule. For the first rule, as I've said, IMD4, IMD5, IMD6, IMD7, they're immaterial. So if they're 0, if they're 1, if they're anything, that has no effect on the CA. So in that sense, 10, rule 10 and rule 90, rule 10 and rule 90, they're equivalent. So I have to start with 10. Okay, fine. So 9, if I start with 90, then next rule is class of R1 is 2. Well, come here, 2. So from 2, 15 is chosen. 15, okay, 15 is there. From 2, I have to go 1. Well, I have to choose rules from here. And 85 is chosen. So come 85. So this 85 is there. Then from 85, what is the class of next rule? It is 2. So my next rule is, or next cell is the last cell. So I have to choose rule from this table. Okay, this is my table. So I'm considering this C. Here 5, 20, 55, 80, these 4 rules are there. So here rule 5 and rule 15 using they are equivalent when they act as last rule. So therefore 90, 15, 85, 15, it is a reversible CA. So that is verified from the from this table. Okay, so this is the reversibility. Okay, in this way, I can, as I've said, I can explore reversibility of. So so I have taken so much time. I have taken already 1 hour. Few more minutes I need. I can. So this tabular represent this table format, this class synthesis, analysis, etc. These are for non-uniform ECA with null boundary condition. So as I've said, I can use periodic boundary condition or other boundary condition, and I can use any number of states. So our reachability tree will help to develop this kind of classes and this kind of table, as well as it will help to design efficient synthesis and algorithms for deciding as well as synthesizing reversible CA. Okay. So this is the importance of reachability tree. I can say it can deal with linear, nonlinear, any kind of CA. Next point was is one class. Another is if I want to deal with the convergence. Can I deal with the convergence property directly? Uh, 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 can I decide convergence of a CA from the tree? No. Reachability tree cannot directly tell us whether a given CA will converge to some fixed point or not. We need to do some further processing. We need some processing. Okay. For that, let us trace predecessor of configurations. Note that we have said that reachability tree, in reachability tree you can see the configuration as well as RMD sequence. And RMD sequence and reachability, RMD sequence and configuration, they form predecessor successor pair that I have said in some slide, right? So I want to use that one here. What I want to do, I want to trace predecessors of configuration. Take as this example, my old CA. So 165, 73, 290. This is the transition diagram I have shown it before, and this is my tree, right? Now I want to trace the predecessor of configuration, right? See here, you can see 0, 0, 0, 0. This configuration is stable. It's very good. I want to find predecessor of this predecessor of this configuration. Similarly, say 0, says say any configuration 0, 0, 1, 1 or 0, 1, 0, 0. Okay, I want to find the predecessor, and what I'll do, I form a link from one edge to another edge. To find the predecessor, I'll form a link. Take an example. Suppose I'm considering this this sequence. S sequence means this configuration is 0, 1, 0, 0, 0, 1, 0, 0. So in my diagram 0, 1, 0, 0, this one you can see here 0, 1, 0, 0. Its predecessor is 1, 1, 0, 0. I want to find predecessor in this in this tree, right? And this is my predecessor. What I've done here, you can see a dotted line. See, from this one I'm writing I'm putting dotted line here. From this edge I'm putting another dotted line, etc. So I am linking the edges, and to link we are exploiting the RMTs. Practically RMTs are used. See, if I consider this configuration 0, 1, 0, 0 is a configuration, and it is associated with one RMT. Which RMT that is? That is 3, 6, 3, 6, 4, 0. Right? 3, 6, 4, 0 is associated with this one. So, or 3, 6, 5, 2 is also associated with this, with this configuration. And I'm tracing this one here. Anyway, to make the story short, so the edges are linked, right? And this link we can develop a logic of developing link along the edges. So there are three kinds of basic links that exist in the tree. One is called forward link. Forward link means if arrow is on right side, if link goes to the right side, backward link if it goes to the left side, and self link if a edge is linking itself. And then I can get a cross link. Cross link is nothing but a cycle, a loop formed by jointly forward link and backward link. Okay, so this is a cross link. You can see this link. There are two way. So from this edge E00, I can go to E01, and from E01 I can come back to E00. It forms a cross link. A theorem is there. A CA contains a multi-length attractor if there exists a cross link among leaf edge. So I have used a term called leaf edge. So edge cannot be leaf edge. So I'm defining here in a different way. Anyway, if a cross link is formed among leaf edge, then we call the CA is having multi-length attractor. Take this example here. So here 1, 2, 3 red lines are there. They are forming a cross link. From this one, you can see my mouse pointer. From this one, I'm going to this, and this edge. From this edge to that edge, and from that edge, I'm coming back to my initial first edge. So a loop is formed. So cross link is there. If I find a cross link in the leaf edge, I'm calling it leaf edge. Okay, this edge is called as leaf edge. So, so if a cross link exists, I can say that the CA contains a multi-length attractor. And this corollary, very interesting. So a CA contains M fixed point. If a CA contains M fixed point, then there exists M self-linked leaf edge. Okay. If I'm having M self-linked leaf edge only, and there is no cross link, it means the CA is having only M fixed points. What is this implication? If my system is having only fixed points, then the C has to converge. The automaton has to converge to that fixed points only. You have no alternative, right? You have only fixed points. Someone have to converge, someone have to come back, you have to come. Where are you coming? So there is only fixed points. So it implies that CA is having multiple attractors, and the CA is multiple attractor cellular automaton. So using this argument, I can develop a decision algorithm. Okay, so first you form a link tree one by one. Okay, like previous way, you get the edges from the root node, then from the next level node, other edges, and each time you develop the links. Each time you develop the links, and in this way you proceed. And then finally, if you see that there is no cross link but only self link, you can decide, you can declare you are having this, the CA is multiple attractor cellular automaton. Okay, so these are convergent CA which can be used for pattern classification or similar applications. Okay, so this is the implication of tree and then link. Okay, so some techniques. So I have not gone through. I'm not discussing in detail. Okay, the point is linked. The edges can be linked to trace the predecessor of configurations, and based on that, we have developed the theorem, and then we have developed our decision algorithm. Okay, then we can decide easily that whether a given CA, okay, so that we can, for linear CA, we have the theory of matrix algebra, right? We can use polynomial theory, but for nonlinear CA, okay, no, you have no alternative. We have no alternative. So tree and link can help us to decide MA CA. So this is about tree and links. Okay, so therefore, how I have started? I have started, there are two type of CAs that I used. One is reversible CAs, convergent CAs. And here I have shown that using tree, we can efficiently decide reversibility as well as we can decide convergence of cellular automata. And for both the cases I have shown, I mean, I have used null boundary condition, but all are possible. I can do everything using periodic boundary condition, and by using the increase of by increasing the number of states. Okay, so reachability tree is a tool, is a good tool to do all these things. The last point is, how can I implement? Since I'm talking about technology, I should say something about implementation of non-uniform CA. I can implement non-uniform CA by writing small code. There is not a big issue. We can write a small code, and we can do it in hardware. We can implement some hardware for, for a given non-uniform ECA. Just to briefly revisit this part. Suppose my CA is 4-cell CA, 150, 90, 150, 90. So it will look like this. So what I need to do to implement a cell, I need this kind of structure. In hardware, I need on flip-flop, which will store the state of a cell, and a combinational logic, which will implement the rule, the nested function, right? So combinational logic will implement the nested function. Since I am using 3-neighbor CA, it will take input from left neighbor, it will take input from self, it will take input from right neighbor. And when clock pulse will come in, its state will be updated. So this is a schematic diagram. So if you have n number of cells, so for each cell, you need a flip-flop, you need a combinational logic circuit. Okay, and you have to repeat it, right? So if you have n cells, so what you need n flip-flops along with combinational logic circuits. So this is very simple implementation. This is the reason why CA cell automata get popularity among the VLSI researchers. So brief about hardware implementation. So 90, so for example, 90, what 90 does, it takes input, left input, takes state of left neighbor, state of right neighbor, and do addition, and then do modulo 2 operation. So this is about rule 90, this is about rule 150. It actually adds. So if it is R, X, Y, Z, so it is actually X plus Y plus Z mod 2. So hardware implementation will be like this. So it will take, so AC is a state at time t. ACE TC, note that what notation I have used here. ACE T subscript I minus 1. It means state of cell I minus 1 at time t. Here ACE T subscript I means state of ACE T is the state of cell I at time t, and so on. So here, using the states of at time t, I am finding state at time t plus 1. Okay, so this is very simple logic which I can get from the given function. Okay, so when rule vector is given, you have to find out this kind of combinational logic, right, for that against that rule, and then you have to implement. So take an example. I shall not, I have taken so much time. I shall not go into detail that I have to implement 165, 73, 290 under null boundary condition. So I have to find out. So this is my table. I have to find out the nested function, nested logic. So this is the nested logic for first cell. This is the nested logic for second cell. So S1 means cell 1 actually. Second cell means cell 1. Okay, and we have optimized all of this. Okay, so this is the rule 200. Next logic for the third rule, third cell, and finally is for rule 90. Okay, so we can use Carnot map to get the next set logic also. So anyway, the point is somehow you have to find out the combinational logic circuit from the given rule, right? If you find them, your task is done. This is hardware implementation. So I have just implemented the hardware. So this is the hardware implementation of 165, the 4 cell CA 165, 73, 290. See, cellulatometer by its nature, it does local computation, it interacts locally. So this is the reason. So people of VLSI domain, they get attracted. So here, wire length. So a cell has to come. You need. A cell has to interact with its neighbors only. Wire length matters in case of VLSI design. How many? What is the length of wire? Since the cell interacts locally always, so length of wire for communicating with its neighbor, it should be always less. This is the reason actually. So there is no long range communication, always communication with neighbors. Okay, and further, you can easily implement them in hardware. Okay, so this is the reason why people get attracted. So non-uniform ECA, they can be efficiently implemented in hardware. Just to conclude, not conclusion, just I want to end here. So many more applications are there. We can many more applications to explore. Okay, I have given only sample samples one. Unreachability tree, it has a great promise to meet all requirements to be an efficient characterization tool. Just two challenges I want to point out here from technology point of view. See, here we have dealt with finite cases. Classical, the mathematicians, the computer scientists who do research with cellular automata, they consider the lattice size as infinite. But in my whole discussion, I have considered lattice size is finite. We have no business. I mean, when we use technology, when we use cellular automata technology, we have no business with infinite case, infinite CA. Okay, but there are many exciting properties which we see for in infinite CAs, the classical CAs. For example, universal computation. It is said that cellular automata they are as powerful as universal Turing machine. Sometimes some people, some researchers say they are at least as powerful as universal Turing machine. But this logic is applicable for infinite CA. May I ask this question here? That is universal computation possible by finite CA? By finite cellular automata, finite non-uniform cellular automata? We don't know. So that may be one good application area that may lead to a new kind of technology. It's possible. And there is the consequence of the first question. Is it possible to develop computer architecture based on cellular automata? If you want to develop computer architecture based on cellular automata, the first requirement is your final cellular automata. They have to be computationally universal. Otherwise, they can be a jailbroker's computer, right? So they have to be computational. I mean, if you want to develop computer architecture by cellular automata, so you have to first show that cellular automata they can do universal computation. The final cellular automata they can do universal computation. I don't know. For this purpose, we can use non-uniform CA, and we may. I mean, we're ready to go beyond one dimension. So all the works which I present here, all are applicable. The reachability tree for one-dimensional CA only. This is not for 2D CA. The applications developed, they are only for 1D CA. So we can go beyond of 1D CA. Is it possible if we go beyond, if we work with 2D or 3D? But the point is, we want to work with finite cellular automata only. So apart from these two challenges, there are many challenges. So here I have written these two. Thank you. So I've taken so much time. Any question you have? I mean,
Hello, dear Sukanta.
oh, yes, nice.
Morning. Thank you very much for this very interesting talk.
Oh, thank you, thank you.
Um, I have some questions.
Uh, sure,
We
sure.
Uh,
No.
when you are speaking about of this kind of reversible cellular automata,
Yeah.
what is the most large cycle found in these roles?
Uh, for non-uniform, I mean linear cell automata. If I consider linear cell automata, so if I have n cell, so maximum possible length is to the power n minus one, to the power n minus one, right?
Okay.
But for that, the theory is that the linear cell automata can be represented by matrix. And if the matrix has a characteristic polynomial, if the polynomial is primitive in the field, then the CA automata, the automaton is maximal length automaton. Okay. So this result is, we are having this result for linear CA. But for nonlinear CA, we don't have such result. Hmm. And we don't know. So if you ask me to give some nonlinear CA, by nonlinear maximal CA by tree, is it possible? Okay, we are working on that, but it's not. I mean, till date we have not. I mean, we can do it.
Okay, in the same direction,
Hmm.
is here a rule with only one cycle?
Sorry, one cycle means?
Yes, is here a evolution rule
No, no,
with
no, no,
only one cycle?
no, no. At least two cycles. At least
Only
two
two.
cycles. Yeah, yes.
Ah, okay, okay, okay.
We have not tried any proof. At least two cycles are there. But from matrix algebra, the proof is very simple. Okay, all zero. I mean, there will be always a single cycle and rest are all the different one. But always two cycles. At least two cycles.
Ah, all right, this is the minimum.
Yeah, yeah.
Okay, okay. Um, when you talk about of this universal pattern generator, do you know
Right.
a universal cellular automata able to construct any pattern?
Yeah, but here this universality with respect to the pattern generation patterns required by test designer. Okay, the VLSI test designer, they need one kind of patterns. Okay, so pseudo-random patterns, deterministic patterns, etc., etc. From that point of view, we have called it universal pattern generator. Okay.
Okay, then this one has a relation with universal constructor
Okay. We have not tried. We have not worked in that direction.
because it is interesting if a reversible cellular automata is able to find a universal constructor.
Okay.
I'm not sure in this direction.
Yeah.
So, okay, another question is again with this universal cellular automata able to construct any pattern. This automaton exists in one dimension?
Yes, yes. We have worked with one dimension
Yes?
only. Yeah, yes.
Okay, it's very interesting. Okay, the last question is, in this kind of reverse automata, you find some rule able to exhibit complex behavior?
Complex behavior. Again, that point not started, but one work we did, the chaos of non-uniform CA. Only one work we did, and they can show. Obviously, the complex behavior they can show, but we have not explored much. Yeah.
Okay, so thank you very much, Sukanta. Very interesting talk.
Thank you, thank you.
Okay. Thank you, sir. Any more question from anyone? Am I audible?
Yeah, yeah, yeah.
Okay. Okay. So if not, then I will ask you one question. Sir, how do you find that class relationship? That which class will direct to the next class? That is this class relationship. How do you find that? What is the way to find that class relationship?
Actually, we have two theorems now that uh, nodes, you know, uh, from say I am at level I. Okay, I know. Suppose it is class is X. From that, I want to find say class of rule I or next cell, so cell I plus one. So using the theorems, I know these are the possible options. Okay, so and these options I can get. Okay, so if I explore those options, then I can get okay from this one. These are possibilities. Okay, so should I go to the slide?
Okay.
Just a minute, just a minute. Is my slide visible?
Yes.
Okay. See here. Oh, sorry. See, you can see here RI 0, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7. Right? This is the class of cell I. And suppose I am saying it is class 1. Why I am saying class 1? There is one issue. So you can see here. You can see. Okay. Say if the nodes are like this 0, 1, 2, 3, 4, 5, 6, 7. If my nodes are like this, then unique nodes are like this. I am saying it is class 1. If my nodes are like 0, 1, 4, 5, and 2, 3, 6, 7, I am saying it class 2. If nodes are like this, two nodes 0, 1, 6, 7, 2, 3, 4, 5, I am saying it's class 3. Now suppose it is 0, 1, 2, 3, and 4, 5, 6, 7. So it is class 1. So from 0, 1 to 3, I am getting one option is of getting 0, 1, 2, 3, and 4, 5, 6, 7. From 4, 5, 6, 7, another option is again getting 0, 1, 2, 3, and 4, 5, 6, 7. So how I'm getting this one based on my rule. So if I know the rule of, if I know the class of I, which is 1, and if I know the rule, right, then I can get next level unique node. What I get here in the in the speaker from 0, 1, 2, 3, 0, 1, 4, 5, 6, 7, I get 0, 1, 2, 3, 4, 4, 6, 7. So means from class 1, I again get class 1. Because 0, 1, 2, 3, 4, 5, 6, 7 is class 1. In this way. Is it okay?
Yeah, yeah. Okay. Understood.
Okay.
Thank you, sir.
Yes.
My question is that this reachability tree is mainly for non-uniform CA, but is it possible to develop a advancement version of this reachability tree for understanding and classify the different kind of problems of convergence and reversibility for asynchronous cell automata?
No, this is developed especially. For reverse. For
If we
sync.
add some probability with
This is developed for synchronous CA. For asynchronous CA, you may try, but uh, the construction is completely for synchronous CA. Maybe for that we'll get some different structure. That might be interesting. We may get different structure.
thank you.
Okay.
Okay, thank you, sir, for the nice talk. Yeah, he sir.
No, I
Sir,
just
I,
also for this very lucid and actually for a person like me could also follow almost say I should say 60% of the stuff. So thank you very much. You could
okay,
touch a little bit of logic because it was almost you were just skirting. It was all, when you showed these mm, last slides, that is the derivation, then you could perhaps mention a little bit about the logical part also. That you developed some kind of logic also there. Yeah, anyway, it was nice.
okay. So let me move to the valedictory session. So, as
Ah,
I declared, today we are going to conclude this first series of webinars that we started on August 16, 2020. We had already 9 sessions of the series where the experts and eminent scientists over the globe in this field have shared their research findings and engaged in lively discussions with our audience. So we had, along with Professor Shukanto Das, we had Professor Dipanita Roy Chaudhuri, Professor Hector Zenil, Professor Shumita Vasu, Professor Kenichi Morita, Professor R. Ramanujan, Professor Gennaro Martinez, and Professor Najim Fritz as our speakers. I want to thank all our speakers who readily agreed to give us their precious time from different time zones of the world and shared their research. We are enlightened by their talk and motivated by their dedication and contribution in their fields. So if any of you have missed the sessions, you can visit the webinar series on the Cellular Automata on the Cellular Automata India YouTube channel that we have created specifically to post about theory and applications of CAs, different related events which is happening around the world, and the discourse of lecture series, webinars, and academic talks associated with it. And we are interested to encourage audience to create further discussions on the post. Today, I want to grab this opportunity to share two people who are the main motivator behind this initiative. First is uh, Professor Mihi Chakraborty, our beloved sir, who is a renowned mathematician and logician of our time, who put the seed of such an idea in our mind. And next is Professor Shukanto Das, our mentor and guide, without whose constant support and motivation, this journey could have been impossible. So first I request Professor Chakraborty to say just a few words. Sir, please.
No, actually, I really wanted such an event take place, uh, and that you have done it is really wonderful, and I congratulate you and your. I don't know who else took part in the organization. If there are anybody else, I also thank them also. Mm, definitely Shukanto, I know that Shukanto was definitely behind all this. So Sukanto definitely deserves a big uh, hand, and um, and I am happy that this thing really could take place, and I am also certain that Kamalika and others, and her friends, and Sukanto himself, maybe um, other people also, those who took part in this particular sense, I think uh, they, they together can build up some kind of network which will be quite fruitful in the progress um, in, in, in development of collaborative research, because uh, this now this opportunity. I mean, we have got this opportunity to develop the kind of collaboration, and it is for sure that nowadays doing something only by oneself is not very uh, not very easy and not very I mean, desirable also. Because I know Sukanto is very much interested in democracy, and he's trying to find out and he has a philosophy that a democracy must be pluralistic. So that means more than one. I mean, uh, one of the I mean commentators was asking for whether there is one cycle, one possible cycle only, and answer is not, at least two. So that that is prophetic in the sense that you cannot live alone. Uh, at least two persons should be there. Anyway, I thank Kamalika, Shukanta, and all others for this. I will have to leave, Kamalika. Please don't mind. And I leave now. Okay? Thank you.
Okay, sir. Okay, sir. Thank you, sir. Sir, I want to ask Sukanta sir if he can say something because he is already tired, might be because he is speaking for 2 hours continuously. But still, if you want to say just a few words.
Oh, thank you. Thank you, Kamalika. So, what Mirza said, Mirza is a initiator in some sense. But Kamalika, what you did is so, you took this initiative. Okay, we
Yeah,
were,
it's a
we are the
joint
leader.
effort.
Right? We are you are the leader. So it's a big effort, a good initiative. And I also hear, uh, I also thank Junaro actually. So Junaro is sitting at Mexico, and at Mexico it is morning, so 6 or 7, maybe 7, yeah. And in almost all sessions he came, and it's so encouraging to us. So Kamalika, I have a Junaro. We're talking about this one. So from other part of this world. So you have joined, and it is very encouraging to us. Okay, so we took
Exactly.
this initiative just so that more people get involved in solar automata research, and we can share our knowledge. We can learn many things from many people. So this platform was created. That was accidentally created anyway, but this journey was fantastic. Okay, fantastic. Different kinds of people talked, and we learned so many things. And the most important thing is, as Kamalika has said, when we approached the scientists, so all of them, almost all of them, accepted. And Morita, Professor Morita, he's 75 years old, and he agreed to come. And at the time it was 10, night 10. Then he was with us and gave lecture. That was so encouraging. So, we get, this is a good experience to all of us. So I hope we'll continue, this journey will be continued. Maybe Kamalika is having some plan. So we want to continue this kind of this kind of journey. And most important thing, what Nida was saying about democracy. So see, Solar Automata is some sense it is democratic, no? See, computing is being done by a lots of cells. They work collectively. So philosophically, that is very attractive to us, all of us. I love Solar Automata is one dozen. Okay. So it's very natural and it's very democratic. And it's not autocratic. It hate autocracy. Semi-automated and semi-automata hate autocracy. So that is the one point of my love. So I want to continue, my research also in this direction. So I hope that we'll take few programs in future, near future, and we can meet in virtual domain once again. Thank you all.
Yeah, thank you, sir. Yeah, I want to ask Professor Martinez also to just share some of his thoughts with us, because he was the constant supporter, and his presence was the biggest motivator for us. Although there is a huge difference in time zone, he was there almost in all of our sessions. So, Professor Genero, if you can speak a little, few words.
Yes, thank you, dear Kamalika. Well, for me, it's an honor to participate in this seminar. So the Indian community in Solar Automata is very productive, and all day always present relevant results. And I will congratulate to all yours, because this is a very nice idea to connect several researchers in Solar Automata. And many congratulations to you, Kamalika, because I think you have many energy to organize all these things. And Professor Sukantadas, that's really very stimulant researcher in Solar Automata. And thank you very much for inviting me, and I am very happy to participate with yours.
Thank you so much, sir. Yeah, sir, everyone is congratulating me, but I'm just the host. So I'm just a face. But behind me, there are these my research teammates from the IST Shikpur, my alma mater. I am thankful to their support and service. And especially, I want to thank Shukarna Di and Debapriya, who have shared many of my duties in several ways. So without them, it would have not been possible. So although I'm just a face, the credit goes to the team. And finally, this webinar session could not have been successful without the participants, so whose presence encouraged us to move forward, to keep on going with the sessions 1 month at a time. So we as the organization, we are grateful to them. And because of you, the participants, we have taken another initiative, just like Shukanta sir said. Yeah, we have a plan. This plan is we are going to start a series on the memory of Professor John Horton Conway, the playful master brains who transformed mathematics. Probably all of you know that he was a legendary mathematician who stood out for his love of games and for bringing mathematics to the masses. He was one of the most versatile mathematicians of the past century, a wizard, polymath, and storyteller, and a natural problem solver whose unassisted feats often left his colleagues unstunned. So he is known for his unbounded curiosity and enthusiasm for subjects far beyond mathematics. He was a beloved figure in the hallways of Princeton Mathematics University building, where he has worked almost until his death. And he was roundly praised as magical genius, who this term that was specifically coined to offer to the Nobel physicist Richard Feynman. So Professor Conway has made several contributions to the group theory, analysis, topology, number theory, geometry, algebra, and combinatorial game theory. But perhaps he is best known for creating the game of life in our field, cellular automata, that he used to call no-player, never-ending game, where collections of cells evolve into new configurations giving some complex structures depending on a very simple rules. He was an active researcher in the Princeton Math department. Even in his 70s, just 2 years ago, he had suffered a severe stroke, and then he was almost hospitalized to the and stayed in the nursing home. But still, he was active. Even I have read that he has even just before his death, 1 week or 2 weeks before his death, also he was actively participating in over telephone with his colleagues on research discussions. So last year, April 11, we lost him due to this COVID. At that time, he was 82. So his legacy of math luminary, we just lost him due to COVID. So as an honor to his work, as a tribute, we want to start a series on the impact of his work on math, science, and several other domains, just like in cellular automata also. So our webinar, this lecture series will start on 10th April 2021, and we plan to have on this month of April only, that is on the 3 consecutive Saturdays. So please join us on that series, and